Consider the problem of a dielectric sphere of radius a in a uniform electric field, along z-axis. We want to know potential everywhere. Problem is one of solving the Laplace equation with the proper boundary conditions at r equals a. We clearly have azimuthal symmetry, so inside, normal phi sub in equals the sum from L equals 0 to infinity of a sub L r to the LTH power p sub L of cosine theta. Outside, normal phi sub out equals the sum from L equals 0 to infinity of open bracket b sub L r to the LTH power plus c sub L r raised to the negative L plus 1 power close bracket times p sub L of cosine theta. The boundary condition at infinity is normal phi vector negative e sub 0 z equals negative e sub 0 r cosine theta. Thus the only non-vanishing b sub L is b sub 1 equals negative e sub 0. The other coefficients are determined from the bc at r equals a.
Tangential e, negative 1 over the fraction with numerator partial differential normal phi sub in and denominator partial differential theta vertical bar sub r equals negative 1 over the fraction with numerator partial differential normal phi sub out and denominator partial differential theta vertical bar sub r equals a. Normal d, negative epsilon the fraction with numerator partial differential normal phi sub in and denominator partial differential r vertical bar sub r equals negative the fraction with numerator partial differential normal phi sub out and denominator partial differential r vertical bar sub r equals a. Let's substitute the series. See the next equation. See the equation shown, from which we get a sub 0 equals c sub 0 1 over a comma a sub 1 a equals negative e sub 0 a plus cp to the negative 2 power comma a sub la to the LTH power equals c sub la raised to the negative L plus 1 power for L is greater than 1.
Thus, a sub 1 equals negative e sub 0 plus the fraction with numerator c sub 1 and denominator a cubed, and a sub L equals the fraction with numerator c sub L and denominator a raised to the 2L plus 1 power for L is not equal to 1, relations I and 2. For the second relation, see the equation shown. Again, have ONLY times B sub 1 equals negative E sub 0. Let's get relations at various L values. See the equation shown. L equals 1, negative epsilon A sub 1 equals negative open bracket negative E sub 0 plus C sub 1 of negative 2a to the negative 3 power close bracket vector epsilon a sub 1 equals negative e sub 0 minus 2 the fraction with numerator c sub 1 and denominator a cubed, relation 3. L is not equal to 1 colon negative epsilon a sub LLA raised to the L minus 1 power equals positive c sub L of L plus 1 a raised to the negative L plus 2 power vector epsilon LA sub L equals negative L plus 1 times the fraction with numerator c sub L and denominator a raised to the 2L plus 1 power, relation 4.
1 plus 3 vector 2a sub 1 plus epsilon a sub 1 equals negative 3 e sub 0 vector a sub 1 equals negative the fraction with numerator 3 and denominator 2 plus epsilon times e sub 0. 2 plus 4 vector open bracket epsilon L plus times L plus 1 close bracket times the fraction with numerator c sub L and denominator a raised to the 2L plus 1 power equals 0. See the next equation. See the equation shown. Thus, equation 6-43 and equation 6-44.
Note that E sub in equals the fraction with numerator 3 and denominator epsilon plus 2 E sub 0 is less than E sub 0 times IF of epsilon is greater than 1 vector potential less inside. Thus E field is partially screened inside the sphere. Outside the sphere the potential is that of the applied field and a dipole moment. Equation 6-45, where the dipole is oriented to oppose the field. The dipole moment can be interpreted as the volume integral of the polarization P, where the polarization is equation 6-46, and the integral from 2 of pdv equals p as expected. For polarization surface charge density, equation 6-47, thus, equation 6-48.
Example 6.2. Consider two concentric conducting spheres, radii a, b, with b is greater than a, with inner sphere having charge q and outer sphere charge q. The hemispherical shell above the xy plane is filled with dielectric epsilon. A, Obtain the E field everywhere between the spheres. B. Calculate the surface charge distribution on the inner sphere. C. Calculate the polarization charge density induced on the surface of the dielectric at R equals A. Solution. A. 1 E field everywhere between spheres. 4. A is less than or equal to R is less than or equal to B, times A and D of 0 is less than or equal to theta is less than or equal to pi sub 2. See the equation shown. 4. A is less than or equal to R is less than or equal to B, times A and D of pi is less than or equal to theta is less than or equal to 2 pi. See the equation shown. Since spheres are conductors, E sub theta must vanish at R equals a comma R equals B. See the equation shown. See the next equation. Same result for two cases. Case 1, A sub 2L. Case 2, B sub 2L. So,
see the equation shown. See the next equation. Assume charge densities sigma sub 1 times A and D times sigma sub 2 on inner surface. Gauss's law. See the next equation. Similarly, E sub 2 equals 4 pi sigma sub 2 A squared, divided by R squared. Tangential E is continuous. See the equation shown. So, for the surface charge distribution on the inner sphere.
See the equation shown. Similarly, sigma sub 1 equals epsilon the fraction with numerator q and denominator open bracket 2 pi A squared times 1 plus epsilon, close bracket. C for the E field. See the next equation. Let's now consider molecular polarizability and electric susceptibility. Molecular polarizability and electric susceptibility. A full analysis of the relation between molecular polarizability and electric susceptibility requires quantum mechanical models. Fortunately, simple dielectric properties can be obtained with the existing classical model. The electric field, being additive, can be decomposed into parts. So, let's split the E field contribution felt at a position x, internal field E sub I, to that of nearby molecules, E sub NEAR, and that of an average background, viewed as macroscopic field, where the background is decomposed into a macroscopic E part and a macroscopic, material polarization part E sub P, due to polarization P. The potential felt at position x is thus decomposed into equation 6-49.
Where the internal field is related to the near field by equation 6-50. Note, we are effectively saying use the improved approximation where the locally variable polarization, giving E sub NEAR, is swapped in for the average background polarization. Consider a spherical volume V equals 4 pi R cubed over 3, total dipole moment in V is equation 6-51. The average electric field inside the sphere due to this polarization, thus E sub P, is equation 6-52. Note the sign change due to definitions in reference to equation 6-53.
Discussed previously, where the latter has alternating signs in the expansion. So, equation 6-54. In most materials E sub NEAR asymptotically equals 0. In a cubic lattice or a completely random, homogeneous and isotropic, there is the exact result E sub NEAR equals 0. So the focus is mainly on P. Now P equals n of left angle bracket P sub MOL right angle bracket, where we now reference the average dipole moment of surrounding molecules, not total like P. If we define molecular polarizability gamma sub MOL, a macroscopic quantity, we can write left angle bracket P sub MOL right angle bracket equals gamma sub MOL times E plus E sub I, which then gives equation 6-55.
Using P equals chi sub EE and epsilon equals 1 plus 4 pi chi sub E, this becomes equation 6-56, or equation 6-57, which is known as the Clausius-Masati equation, at optical frequencies epsilon equals n squared, and this is then known as the Lorentz-Lorenz equation.